Hey guys, welcome to your next tutorial. Today we're going to be learning about Timestep, what it is, and we're going to actually program it into our game. But first let me show you why we need it. I've got the FPS set to 60 right here, but because of my screen capture program, we're going to probably be running at about 30 FPS. Yeah, definitely. So as you can see, we're moving really slowly. Now, if I wasn't using the FPS capture program, we would actually be moving twice as fast because we'd be getting 60 frames per second. The game is designed to run at 60 frames per second, but since we're having a little bit of lag, maybe we're drawing too many things, or we're using a screen capture program, so we're running at 30 FPS, we shouldn't be, adversely affecting the user's gameplay experience based on his FPS. It should pretty much play exactly the same. It shouldn't go in slow motion. And that's because we don't have any time step right now. We're not using a time step. So what a time step is it's a way for you to deal with loss of FPS and make it so that your simulation runs more or less the same. So let's go ahead and draw a little bullet. So here I have a little XY coordinate plane, and here's our bullet. And let's say it's moving to the right, just like this. And normally it's going to run at 1 meter per second, or meter per frame. That's pretty quick, but it's a bullet. All right, so it's moving to the right at 1 meter per frame, and this is how fast it should move at 60 frames per second. However, if we are running at 30 frames per second, then we should not move to the right by 1 meter per frame. We should actually move to the right by 2 meters per frame. Since we're moving at, twice the normal speed, then if we're running at half the frames per second, it's going to be pretty much the same. So there's 3 different ways to do this. There's a variable time step, there's a semi-fixed time step, and a fixed time step. So first let's talk about the variable time step. This is the easiest one to implement. Now with a variable time step, what you're going to do is, if you're running at 30 frames per second, what you're going to do is just take all of the motion in your game, everything that's doing any physics, and multiply the movement by 2. So what we're going to do is take our 1 meter per frame, and we're going to multiply by 2, and then we're going to be moving 2 meters per frame. And the way you calculate this is you have a desired FPS, basically, and we're actually going to use frame time, not FPS. So you have a desired FPS, we'll say this is like 60, right? And then you have an actual FPS, say this is 30. Well, the way you're going to calculate this time step variable, which is called the delta time is what you're going to multiply by all of your motion, is like this. You just say delta time is going to be equal to, and then you take your desired FPS divided by actual FPS, which is going to be equal to 60 divided by 30, which equals 2. And that's how we get multiply by 2 if you're only getting 30 FPS, but you want 60 FPS. Now, if we're running at 120 FPS, say we're running even faster than we're supposed to, we don't want the game to run faster, and this math is going to ensure that our delta time is 0.5. So all of our motion is actually going to move half as fast. So in the bullet example, if we're running at 120 FPS, instead of going 1 meter per frame, we're going to do half a meter per frame. So what's the problem with fixed time step? Well, there is a pretty big problem. Let's say we are going 1 meter per frame at 60 frames per second, but then we drop to 20 frames per second. Well, that's going to cause our multiplier to be 3. So we're going to have a really, really big motion in one frame, like this. But say we have a wall, and our wall is right here. Well, what's going to happen is our bullet, which we have right here, if it was running at 60 FPS, it would have collided with the wall, that'd be fine. But since we're running at 20 FPS, we're going to move 3 meters. So we're going to take our bullet, cut it, and paste it over here. It basically teleports through the wall and we get no collision. That is not good. So that's the main problem with variable time step. There's actually a better way to do this. Instead of using a variable time step, what we can do is ensure that we never go faster than 1 meter per frame. And this is by using a semi-fixed time step. What we're going to do is if we get, say we have 20 FPS, that means we need to move 3 meters. What we're going to do is we're going to simulate this in 3 steps. We're going to do a step where we move here, and that will cause that collision with the brick wall in the previous example. Then we're going to have a step where we move here, and then we're going to have a step where we move here. Semi-fixed time step is a pretty good one. It's not deterministic, which fixed time step is deterministic. And deterministic means it's always going to be exactly the same. If you were doing some complex physics simulation and you needed it to be exactly the same every time you ran it, or if you wanted to have some kind of replay function that was, always exactly the same, then you would want to use a fixed time step. And a fixed time step is kind of like a semi-fixed time step, except it guarantees that you're always taking the exact same steps. We are going to use semi-fixed time step because it is perfectly fine for our needs. I will put a link in the description that talks about all three of these and shows implementations for all three of these. But today we are just going to implement the semi-fixed time step. I hope this makes sense. If you have any questions, feel free to ask me in the description. Let's go ahead and get started implementing this. So there's going to be a few changes we need to make to our code. First, we need to add the ability to pass in a delta time to our update functions. And our two update functions that are moving things around are update agents and update bullets. So let's go ahead and go into main.game.h and add those. So we're going to need a float delta time. This is the multiplier that we're going to multiply by all of our motion. And we'll do that for update agents and update bullets. So let's go ahead and go here. This is asking for delta time. We'll come back to that. Let's make sure we put delta time in the actual function declarations or definitions. Come down here, delta time. I spelled that wrong. Delta time. And then the update agents function is going to call a bunch of other update functions. It's going to update the humans. It's going to update the zombies. And the player, and all three of those need to get the delta time variable passed into them so they can multiply it by their motion. So let's go ahead and do that. Let's go to player.h. So player has an update function and it is overriding the, I believe, human update function. So let's go ahead and do the human one first. Header files, human.h. I need to zoom in so you guys can see. Hopefully you guys have been able to see so far. Sorry about that, I always forget. Okay, so the human update function, it's got this little virtual void here. We're just going to add another parameter, float delta time, and let's go ahead and put that in the CPP file as well. Here's the update, float delta time. And what are we going to do with this? Well, here we have position equals direction times speed. All we have to do is multiply that by delta time. It's as easy as that. So now we need to take this and we're going to go back to, what was it, player.h. And this is probably going to give us an error now, unless this is also overriding the agent update. It is. So we need to make sure we go into agent and also do delta time. For completeness, we should definitely go into human.h. This wasn't going to give us an error, even though we were supposed to be overriding that, that agent function. So make sure you put override here. It's a helpful C++ keyword, remember, that makes it less bug prone. It makes sure that you definitely are overriding a virtual function of the base class agent. All right, so back to back to player. Where are we? I'm getting lost. Player.h. All right, so there's the float delta time there, and now we need to go in here and do float delta time here. And just like before, all we do is anytime we see speed, we multiply that by delta time. So anytime we're changing the position. So all four of those spots right there. And anything else happening here? No, that looks good. We should definitely, let's see, where do we do the frame counter for bullets? We're going to have to come back to the gun. The gun isn't going to be using our time step just yet, but we'll come back to that. Let's go to zombie.h. Zombie.h should see how we're not getting an error here. This should be override. And now it's going to give us an error because we do want to override something. So this is float delta time. And if we go to zombie.cpp, we'll add that in there as well. Why was that giving me an error? No reason. Here's the update function. We'll go ahead and do float delta time. Float delta time. All right, and finally we can multiply delta time here times delta time. There we go. So now our delta time will be applied to all of our agents. We also need to apply it to our bullets. So let's go ahead and do that. And if we go to main game, update bullets, let's see, here we have this bullets.update function. Let's go there. So here is the definition and here's the declaration. All we just need to do is add float delta time and do that in the CPP file as well. Copy that. I'm going to drag this over here. Update delta time and position plus equals direction times speed times delta time. Great. Now we need to go to main game and make sure we're passing everything in. So we just need to make sure we put delta time here. All right. Anything else there? Nope. Go to agents update and we're going to need to pass in delta time for all of these. And we'll do 1, 2, And that looks like it. Where do we update the player? It'll give us an error. I forgot where it was. All right. So now we need to actually calculate what our delta time is going to be. So what we need to do is determine how many milliseconds each frame is taking and use that. We're not actually going to use the FPS because remember the FPS is like the average FPS. It isn't exact. So what we're going to need to do is here in the main game loop, we're going to need to calculate the exact change in frame time so that we can use that to do the actual delta time calculation. So first let's put our desired FPS, which is our desired frame time. So const float desired frame time. Now frame time is the number of milliseconds it takes to do one frame. Now before we set what that is equal to, let's have another const float. And this is going to be called milliseconds per second. This is just for convenience. So milliseconds per second is 1,000. You want to avoid having magic numbers. Like if we just randomly put 1,000 in here somewhere, nobody would know what that means. But if we give it a name like milliseconds per second, then people will know what it means. So our desired frame time is going to be milliseconds per second divided by the number of frames per second that we want, which is going to be 60 FPS. So let's make another const float, desired FPS. And for that, we will do equals 60. There we go, no magic numbers. Awesome. So here is our desired frame time, and we're going to use this with an actual frame time to calculate the time step. So to get the actual frame time, first what we need to do is get the current frame time. So we need to have a float, const float current frame time. And this is going to be, this should actually be current ticks. And this is going to be equal to SDL get ticks. Now remember, SDL get ticks returns the number of milliseconds since SDL was initialized. So this is just going to give us a little timestamp, basically, at this point. And we don't actually want it to be constant. This is going to keep changing. Now, at the end of each frame, or at the beginning of each frame, we need to actually calculate how much time has passed. So let's do that here. We're going to have a float frame time equals SDL get ticks minus current ticks. And this should actually be, we'll call this previous ticks. That sounds better. Previous ticks. So this is the ticks of the previous frame. Sorry, lost OBS there for a second. So what we want to do here is actually store the previous ticks as the ticks of the previous frame, and doing it this way isn't going to really let us do that. So what we need to do is make a new float. We'll say float new time, or new ticks, is going to be equal to SDL get ticks. And then here we can say frame time equals new ticks minus previous ticks. And then we can say previous ticks equals new ticks. And this will allow us to keep track of the ticks of the previous frame and the ticks of the current frame. Now what we need to do is calculate the total delta time from this so we can use it for our semi-fixed time step. So we're going to say float total delta time equals. Now before, when we were in our little example, we used FPS to calculate it, and it was going to be desired FPS divided by current FPS. But since we are using frame time, which is the milliseconds per frame, instead we're going to actually do it the other way around. It's actually the frame time is inversely proportional to the FPS, which means as your frame time gets bigger, basically as your frames take more time, the FPS gets smaller, which is why we're kind of flipping this around. So what we're going to say here is frame time divided by desired frame time. And that's going to give us the total delta time. So if we're running at 30 frames per second, our total delta time will be 2. If we're running at 120 FPS, our total delta time is going to be 0.5. All right, so now we need to use this total delta time down here when we update our agents and our bullets to do the simulation and do multiple steps. So we're going to obviously, since we're doing multiple steps, we're going to need some kind of loop. And for this, we're going to use a while loop. And what we're going to do is we're going to say while total delta time is greater than 0.0f. Now the reason we're doing this is because what we're going to do is loop through and deplete this total delta time. Let's say the total delta time is 3. If we go to our little example here, the total delta time is 3 because we have to take 3 steps. What we're going to do is each step we're going to reduce it by 1. So it'll be 3, then we'll go 1 meter per frame, it'll be 2, then it'll be 1, and once we get to 0, we're done simulating this frame and we can render. Now there is one issue with this. If our simulation is CPU bound, say we have a ton of people, we're going to get what's called a spiral of death, where we just keep trying to simulate more and more frames and we never get to render just because our simulation is taking so long. So what we need to do is limit the number of frames that we can simulate. So let's make another constant int up here. Const int max, we'll say max steps, or max physics steps, that's fine. And we'll set that equal to 6. We shouldn't want to simulate more than, really probably 5. We wouldn't want to simulate more than, no, we'll go 6. 6 steps, if we're taking longer than 6 steps, we should just go ahead and slow down the game because it's better than getting a spiral of death. So let's put an int I here, and we'll set that equal to 0. So then we're going to say while total delta time is greater than 0 and I is less than max physics steps. And then down here we'll do an I++. That'll just protect us from that spiral of death, which you can read more about in the link in the description. All right, so now we need to calculate what our delta time is going to be. So we're going to say float delta time. And for this, we're going to say whichever is smaller between total delta time, total delta time, and the desired, or the max delta time. Now we haven't actually calculated the max delta time. Let's go ahead and do that. Const float max delta time, and that's just going to be 1.0f. We're not going to ever want to do more than 1 in our delta time steps. We're only going to want to do 1 or smaller. So this min function is undefined. I believe it's in C standard library. Include cstdlib. Let's find out. All right, let's try one more. Let's try CMath. Oh wait, algorithm. That's what it was. Right. Oh, std min. There it is. All right. So this is going to get our delta time. Now, if we're running at like 120 frames per second, then the smaller of the two is going to be total delta time, because our total delta time is going to be 0.5, so we'll simulate half a step. However, if we're running slower, say we're running at 30 frames per second, then max delta time is going to be smaller, which is 1, because total delta time will be 2. So we're going to pass in delta time to these two functions to do our actual simulation. And then what we need to do is deplete total delta time a little bit. And what we're going to do is subtract delta time from total delta time. So we're just going to say total delta time minus equals delta time. Now I'm going to put a link in the description with the source code, and I will add comments. There's no comments here. I'll be sure to comment the hell out of it for you. All right, and that is that. So this is our semi-fixed time step. This should work perfectly fine. Let's see what happens. Hopefully nothing crazy happens. Let's see. If this is 0, let's make sure. If frame time is 0, good. We will not get a divide by 0. Whoa, there we go. As you can see, we are moving faster. Even though we're moving at 24 frames per second, our simulation is actually running as if we were at 60 frames per second. We're just rendering slower. So now we have a semi-fixed time step. Everything is really cool. You can read more about it in the description. We should probably, let's go to gun and see if that won't be too difficult. Gun, fire. So where is this? We have, here we go, fire rate. So we have frame counter. Instead of frame counter, let's make frame counter a float. That way, we can say frame counter plus equals 1.0f times delta time. That way we can take into account delta time when we're also firing our weapon. So let's pass in float delta time there, because it is important that all of our physics updates and everything are running according to the delta time. And let's go back to gun update. Float delta time, there we go, and then this is going to happen, I believe, in player.cpp. We just need to pass in delta time to gun update. Am I missing it? I'm just going to run it and it'll take me where it was. I always forget where everything is. Gun update does not take 4 arguments, so we go to error list, double click there, and it's right here, right in front of my nose. Delta time. All right, let's run it one more time. Now our bullets will also be fired at the correct rate. Awesome. It looks like it's firing a little bit faster than it was. And die, zombies. Having so much fun with this. All right, thanks for watching this video, guys. Hope you learned a little bit about delta time. If this confused you, please let me know. And if you are confused, also try downloading the source code that's in the description, because it will have some comments that will explain this stuff. All right, bye, guys.